From self-driving cars navigating our busiest streets, to virtual assistants managing our daily lives, and even to algorithms diagnosing diseases faster than human doctors, artificial intelligence is no longer science fiction. It's woven into the very fabric of our world. But this revolution didn't happen overnight. To understand where we're going, we first have to ask, how did we get here? Our story begins not with silicon chips, but with a question posed by a brilliant mind. In 1950, British mathematician Alan Turing, a man instrumental in breaking Nazi codes during World War II, proposed a test for intelligence in a machine. He called it the imitation game, now famously known as the Turing test. Could a machine's responses be so human-like that a person couldn't tell the difference? This profound idea, conceived amidst the whirring gears and vacuum tubes of early computers, laid the philosophical cornerstone for everything that would follow. It was the spark that ignited the quest to create a thinking machine. Just 6 years later, that spark caught fire. In the summer of 1956, a small group of America's brightest scientists gathered at Dartmouth College. It was here, during a 2-month-long brainstorming session, that the very term artificial intelligence was officially born. They weren't just dreaming, they were drafting the blueprint for a new field of science, convinced that every aspect of learning and intelligence could be so precisely described that a machine could be made to simulate it. Their optimism was infectious and kick-started a golden age of discovery. The years that followed were filled with groundbreaking achievements that seemed to pull the future into the present. Programs like the General Problem Solver, developed in 1959, could tackle elementary logic problems, mimicking human reasoning. Then came Shaky the Robot in the late 60s, the first mobile robot to reason about its own actions, as it cautiously navigated a room, analyzing its surroundings and planning its path. It was a physical manifestation of AI's potential, a real-world entity learning and acting on its own. For a moment, it felt like anything was possible. But the initial wave of excitement couldn't last. The promises made were vast, but the computational power of the era was limited. Progress began to stall, and the complex challenges of true intelligence proved far more difficult than anticipated. By the mid-1970s, government agencies and investors grew skeptical, leading to a period known as the first AI winter. Funding dried up, research labs were shuttered, and the once bright promise of AI was met with widespread doubt. The dream, it seemed, was put on ice. Just as the field appeared frozen, a thaw began in the 1980s with the rise of a new, more practical approach: expert systems. Instead of trying to create a general human-like intelligence, these programs focused on capturing the knowledge of human experts in a specific, narrow domain. They acted as powerful digital assistants for doctors diagnosing infections or for geologists identifying mineral deposits. This commercial success reignited interest and investment, proving that even a narrow form of AI could be incredibly valuable and pulling the field back from the brink. This revival set the stage for the next great leap, a new paradigm inspired by the very structure of the human brain itself, a complex, interconnected web of artificial neurons, learning from data in a way no system ever had before. Imagine a web of interconnected nodes, simple processing units that, like the neurons in a human brain, could learn. This wasn't about programming intelligence line by line. It was about creating the conditions for intelligence to emerge on its own. This radical shift was championed by a small group of thinkers who refused to let the dream die. Pioneers like Geoffrey Hinton, working from their university labs, held a core conviction: the only way to build a truly intelligent machine was to make it learn like a child. They believed that instead of feeding a computer a dictionary to understand language, you should show it millions of examples and let it figure out the patterns for itself. This philosophy stood in stark contrast to the prevailing wisdom of the era, setting them on a collision course with the established AI community. Their crucial breakthrough came in the form of an elegant algorithm called backpropagation. Picture our neural network trying to identify a cat. On its first attempt, it might guess dog. Backpropagation is the process of telling the network, "No, that was a mistake." The error signal travels backward through the network, from the output to the input, slightly adjusting the strength of each connection along the way. It's a gentle nudge, a tiny correction. But repeat this process millions of times with millions of images, and the network slowly, almost magically, learns to distinguish cats from dogs with incredible accuracy. It learns from its mistakes, refining its understanding of the world with every single iteration. Despite the promise of this breakthrough, the world wasn't ready. The late 1980s and early 90s brought what's known as the second AI winter. The initial hype had faded, and the computational power needed to train these networks simply didn't exist. Funding dried up, and many researchers abandoned the field. It seemed as though the dream of learning machines was once again destined for the history books. The pioneers, however, kept the faith, continuing their work in relative obscurity, convinced that their moment would come. And it did, not with a single invention, but with a perfect storm of technological advancement. The explosion of the internet created a resource previously unimaginable: big data. Suddenly, there were billions of images, texts, and sounds available online. The perfect training material for hungry neural networks. Simultaneously, the video game industry was driving the development of powerful graphics processing units, or GPUs. These chips, designed for rendering complex 3D graphics, were coincidentally perfect for the parallel computations required by neural networks. The two key ingredients, massive datasets and immense computing power, had finally arrived. The moment of vindication came in 2012 at the ImageNet competition, a contest to see which program could best identify objects in a vast library of images. A deep neural network developed by Hinton's team didn't just win, it shattered all previous records. It achieved a leap in accuracy so profound that it shocked the entire field. This was the starting gun for the deep learning revolution. The world took notice, and the technology that had been simmering in academic labs for decades suddenly exploded into the mainstream, powering everything from facial recognition to language translation. But the story doesn't end with mere recognition. These networks began to do something no one had anticipated. They started to create. AI began generating photorealistic images, composing hauntingly beautiful music, and writing surprisingly coherent text. The machine was no longer just a tool for analysis. It was becoming an artist, a creator in its own right. This raises a profound new question, one that will define our future. What happens when our creations begin to create for themselves? Artificial intelligence was a master of imitation. It could recognize our faces, understand our words, and even beat us at our own games. But it was always analyzing what we had already created. In the late 2010s, that all changed. AI didn't just learn to recognize the world, it learned to create worlds of its own. It made the generative leap. Sleek, futuristic animations begin to illustrate complex neural networks. The camera zooms into one specific model. The revolution began with a deceptively simple name: the Transformer. This new architecture didn't just process information in sequence. It introduced a groundbreaking concept called the attention mechanism. Imagine an AI reading a sentence. Instead of just looking at the next word, attention allows it to weigh the importance of every single word in relation to all the others. Animated lines connect words, glowing brighter for stronger relationships, showing how the AI grasps context, nuance, and meaning in a way that was previously unimaginable. It could finally understand not just the words, but the story they told. A dynamic timeline appears on screen, showing a graph line rocketing upwards. Logos for GPT-2, GPT-3, and GPT-4 flash by. This breakthrough unlocked the door to a new era, the age of large language models, or LLMs. The GPT series, for example, saw its power grow exponentially. We can visualize this growth not just in performance, but in parameters, the internal connections the model uses to learn. What started with millions of parameters quickly exploded into billions, and then trillions. Each leap in scale brought a leap in capability, transforming these models from simple text predictors into powerful engines of reasoning and creation. The digital brain was getting bigger and smarter at an astonishing rate. The screen splits. On one side, a simple text prompt is typed, "A majestic lion wearing a crown made of stars, photorealistic." On the other side, that text magically morphs into a stunning, high-resolution image matching the description. Another prompt appears. Write Python code for a simple weather app. Lines of perfect code instantly generate. But this generative power was not confined to language. The same core principles were applied to other domains with spectacular results. Text-to-image models like DALL-E and Midjourney began turning simple phrases into breathtaking works of art, blurring the line between human and machine creativity. AI could now compose music, write functional software, and even design complex molecules. It had become a universal tool for creation, limited only by the human imagination that guided it. The scene shifts to a montage of diverse, everyday people. An independent artist uses a tablet to generate concept art for a comic book. A student gets help from an AI tutor to understand a difficult physics problem. A small business owner uses AI to draft marketing emails. Perhaps the most profound shift was not the technology itself, but its accessibility. Suddenly, these immensely powerful tools were no longer confined to billion-dollar research labs. They were available through simple web interfaces and apps, running on the very same devices we use to browse the internet. This democratization put the power of creation into the hands of millions, unleashing a wave of innovation from artists, entrepreneurs, and ordinary people who could now build things that were once impossible. The tone shifts slightly, becoming more contemplative. Juxtaposing images appear. A painter at an easel next to a screen filled with AI art. A team of software developers coding next to a single person using an AI code assistant. Naturally, this sudden disruption sent shockwaves through society. Creative and technical industries, once thought to be safe from automation, were now facing a paradigm shift. The role of the human artist, writer, and programmer was being fundamentally questioned. Was this a tool that would augment human ability, or one that would replace it? The debate had begun, and the answers were far from clear. The final shot zooms into a mesmerizing abstract visualization of a neural network, a glowing, impossibly complex digital brain. The connections pulse with light, but their inner workings are opaque and mysterious. Yet, beneath all this power lies a deep and unsettling mystery. We've built these incredible minds, but we don't fully understand how they arrive at their conclusions. It's known as the black box problem, and as these generative models become ever more capable, they force us to confront the ultimate question. What is the path from this? A machine that can create, to true artificial general intelligence, a machine that can think,